Oh, the clock strikes 12:02. That's our, I think that's our cue. Still see some more people rolling in here, but we'll go ahead and get started. Just want to say welcome, everybody. My name is John Neeson. I'm a new sales engineer here at Dorse. Working alongside Chris and Scott. You see there, you're probably more familiar with their faces. But we got a lot of fun stuff to cover here today. We got Greenheck's own Phil Stazak here. You guys are going to love this presentation. He's got a lot of stuff to talk about, and like he said, we better get started so we can get to all of it. So today we're going to be talking about makeup air, and if you guys have questions throughout the presentation, go ahead and drop them in the chat, and I'll be monitoring that. And maybe we'll probably bring up most of them as they come, but maybe I'll save some towards the end. So stick around to the end there. And with that, I think I'll let you go ahead and get started, Phil.
All right, sounds good. Well, thanks for the intro here. And yeah, that's kind of a joke. So I hope I don't take you guys much longer than an hour, but I do have some passion for this subject. And I got some decent information to share here, but I will definitely try and leave some room for questions in the end. And yeah, if anything comes up here during the presentation, obviously interrupt me, let me know, and then we can address it at its point too. So I'm going to try and share my screen here and kind of go through our PowerPoint, and we'll get this started. A little background on myself. Phil Stazak. I've been an application engineer for Greenheck now. I'm going on year 17. So humble beginnings for myself, though. I started actually in manufacturing. Did 7 years. I was a union guy. Did a lot more with the DOAS and refrigeration background. And then 4 years technical support, so helping start up equipment and troubleshoot units. And now for the last 10 years, or 7 years, I should say, been more on the application side. So helping Chris with Dorsey and all of our mechanical reps throughout the country kind of lay out and understand makeup air ventilation and direct gas fired, indirect gas fired, steam, all the various applications and where we're going to tie in. So somebody had already addressed, kitchens. We'll talk a little bit on general applications and where we're going to see this stuff. So here's the course objectives. Biggest change, I think, with makeup air as far as a technological advance. And one thing that we're pretty excited about as a manufacturer is just the overall how we're bringing in outside air. Overall technology with direct gas, indirect gas, and electric heater, that technology has pretty much been there from the get-go. But as far as how we're bringing in that outside air, the shift toward direct drive fans, we'll kind of talk about some of the benefits there. Talk general heating and cooling with makeup air, much different. We'll talk briefly on cooling, but heating is really the primary focus. Cooling is more on the DOAS side of things, so a dedicated outdoor air system where it's more about people versus a process. So we're talking about process exhaust and then therefore making up for that process exhaust. So cooling is more of a luxury item, really designed for more of the kitchen market than anything else. But heating, even if we have an environment, you guys are cold enough where you guys are located in the country, if you ever risk freezing pipes, even there might not even be people in that space, but you may need to discharge, say 45, 50 degrees just to prevent anything from freezing in that space. So, but then there are spaces where you want to do just general tempering to 65, 70 degrees. So we'll talk the basic heating functions and spend more time on that. And then at the end here, I'll talk about makeup air application considerations. Things to talk about as far as where direct gas is actually can be a dual purpose unit where we're introducing high volume outside air at elevated temperature to space heat. So for large warehouses and distribution centers, things like that, we'll kind of talk about general applications. And then we'll talk about some of the controls things that we have just introduced as a manufacturer, some of the big changes even here in April that we have pretty exciting to actually talk about here. So, all right, so as far as makeup air and what exactly we're talking about, so somebody again brought up this example earlier. So kitchens, the humble beginnings for makeup air, and the one that kind of sets, I think, the story straight for all of us because we can all relate. You walk into a restaurant or a kitchen and you've got either the door cracked open for you where you have an extreme positive pressure in that space, the makeup air is probably running, and there's an imbalance in the system where the exhaust system is down, and you can smell everything that's going on in that restaurant. The reverse scenario, if that door is kind of suctioned closed and you have to tug on that door a little bit to get it cracked open, then you feel that rush of air as you do open that door. Probably the better scenario, because at least you're getting all of that exhaust, that kitchen grease laden air out of your space, but you've got an extreme negative in that space. So every nook and cranny, that's the purpose of makeup air. So it's really just to balance out that airstream. You want a slight negative in some cases, a slight positive in other cases, but we're making up for whatever that process exhaust is. And since we're bringing in 100% outside air to make up for that, we're going to want to temper it in one way, shape, or form. We're not always a perfect condition outside, and we're aiming for, in a makeup air, especially a kitchen, 60 degrees is usually plenty. More focused on the cooling side for a kitchen because of the heat gain in a space than anything else. But again, heating the primary function. Industrial applications, even here at Greenheck, we see this exact example where you might have multiple exhaust fume hoods. In this case, it's weld bays, multiple exhaust fans, one makeup air unit. How do we interlock that? What's the sequence look like? This is a typical application where building pressure would be great to be used, where the loss in pressure in that space, the makeup air therefore is going to respond, whether it's doing recirculation or a variable volume. You want to maintain maybe a slight positive pressure in that space. As one exhaust fume hood is energized, that pressure is noticed, that difference in the space. Therefore, fan speed can ramp up, or we can change a damper position to bring in more outside air to keep that pressure in that space. Also very common for in that particular scenario where we're trying to keep a positive pressure for warehouse design as well. So we'll talk about space heating as far as a superheated green heat unit, and then we'll also just talk about a general application for a recirc control unit where we're doing building pressure as well. And that's where warehouses come in. Again, we'll focus on this a little bit more toward the end of the presentation, but a couple different approaches here. Heavily favoring direct gas fired heat, superheating that outside air, 0 degree entering, 140 degree leaving air temperature to effectively do two things. We're bringing in fresh air when the unit is energized on to satisfy a space condition, and we're going to superheat it to typically 140 degrees, satisfy the space condition, and then disable. Another option is doing a recirculation option, whether it's with an electric heat, indirect gas fired heat, or direct gas fired heat. And in that case, you're just trying to aim for whatever discharge air temperature that you're trying to maintain in that space for a general space condition. So 65, 60, maybe just a freeze condition. Guys driving around, a couple guys driving around with a forklift, maybe can wear a jacket. 55 degrees might even be the general acceptable level there. But in that building pressure scenario, we can do a recirc unit and provide just the discharge air temperature desired for that space. And then the unit is running constant. So you're always churning air throughout that facility. And then the only time you bring in more outside air is when that pressure is lost in the building because a dock door opens up, usually not tied to exhaust systems at all though. So general warehouse ventilation, a little different than typical makeup air, but we can utilize the same units to kind of do a dual purpose unit there. Okay, I'm not sure how that happened. Sorry, guys. All right, so this gets me to probably the more important and one of the biggest changes that we've seen as a manufacturer is shift in the way that we're moving air. So housed fans, everybody's probably pretty familiar with the forward curve belt driven housed fan style. Used to be all favorable on price. You had to build this fan though in a certain arrangement in order to get end discharge, top discharge. We're seeing a shift in the market, and as a manufacturer, all the way up to 25,000 CFM at Greenheck, we have standardized on these direct drive plenum fan offerings now. So fan scroll housing, you're pressurizing the actual scroll itself and generally belt driven. Where now with a plenum fan, you're actually pressurizing a cabinet. So almost endless discharge arrangements that you can do. And with direct drive fans, a lot less maintenance required because there's no more belts and shivs to adjust. You've got a wheel mounted directly on a motor shaft, and then variable frequency drives are typically standard with those, where it would be an option to select with a forward curve belt driven fan option. And then other things that we kind of see here as far as benefits on the plenum fan, I mentioned this already, that scroll fan needed to be built in a certain arrangement and you were limited to either end, top, and bottom. With a plenum fan, since we're pressurizing the cabinet, basically just give us an opening and now we can do left and right side discharge as well. And in some cases, say we make a mistake, the unit is ordered as end discharge, gets out into the field, and you say, you know what? It would be really nice if we could actually turn this unit sideways and come out the side. Most of those panels are typically interchangeable, so you can just swap the panels out. Opens up your discharge arrangements and your flexibility in the field. Okay, so other thing to discuss is the overloading aspect of fans and kind of the victims that we all are in the design side. I'd be surprised how many jobs come across my desk laid out at a 1/2 inch of external static pressure or a 1/4. Seems like there's general rules of thumb always kind of laid out with these systems, but it's not always the case that, especially with makeup air, there's usually very little resistance on the discharge end of these, so very little external static pressure. Obviously, that's not going to be the case every time, but if you don't have any ductwork hooked up to these systems, say even if you have a factory provided 3-way or 4-way diffuser, as a manufacturer, we calculate that static pressure into the system already. So that system, if it's ordered at 10,000 CFM, should actually be ordered if it's going to be a through wall design and the weather hood is just simply extruded on the outside of the unit and then we're just throwing air into that building. We're going to want to make sure to lay out that system at 0 inches of external static pressure because there's nothing else for the unit to overcome. But unfortunately, we see this all the time where, ductwork or safety factors are kind of built into it, or just throw a 1/4 inch on it as a just in case. The problem is we set up the unit to hit the certain fan RPM and hit the design CFM that it was actually selected at. So we're trying to account for that static pressure. And if it's not there, this is an example of a forward curve fan. The blue line is your system curve. Your operating point is the circle. So if we take a look at perfect scenario, real world situation where, all right, we've calculated our static pressure and our system now with internal static pressure and external static pressure, we're just under 2 inches total water column, and we want to move 10,000 CFM. Now we follow that line down to the dashed black line. That's where our brake horsepower is going to be. So for this particular forward curve fan at just around 2 inches of total static pressure, it's going to require right around 8 brake horsepower to move that airflow at 964 fan RPM. Real world scenario though is, all right, we calculated for a 1/2 inch of static pressure that actually doesn't exist. So now we set that unit out on our rooftop, and naturally we're going to move more airflow than what was originally laid out or designed because it was laid around 10,000 CFM. It doesn't have that resistance to overcome on the other end. So now we're moving more closer to 12,000 CFM. And then with a traditional forward curve fan, it is a overloading design. So now we trace that up and we're moving more airflow and we're right at that 10 horsepower. So at original selection, we were at 8. Probably felt pretty confident laying that system out with a 10 horsepower motor. Well, now you're right at the FLA or the overload state of that fan. So now good luck even getting an air balance done to calculate that you're just under 12,000 CFM to dial that system back with that static pressure not being present. So it risks an overload state. This is where VFDs really become crucial to be able to just dial in an air balance with just simple parameter changes rather than changing out belts and shivs. But again, it's just trying to understand that sometimes static pressure, we're over designing or over calculating for some of these systems. Now, the benefit of moving to a BI or an MF mixed flow plenum style wheel is that same design now at 10,000 CFM, just under 2 inches of total static pressure. Now we follow that brake horsepower line. We were at 8 horsepower just as a standard design. The huge benefit of this fan type already is now we're moving significantly less brake horsepower at the same design with this fan type. So you're just under 6, so you can confidently lay out a 7.5 horsepower motor where you were forced to a 10 horsepower motor right out of the gate with that belt-driven fan option. Now that same scenario exists in here, in this case, where 1/2 inch of static pressure maybe doesn't exist. Well, we're moving more airflow than design, right around that 12,000 CFM. but the fan curve and the brake horsepower curve kind of breaks the standard laws that we're used to. Believe it or not, we're moving more airflow than design with less resistance, but we're actually moving less brake horsepower. So it can easily be balanced. You're not in that overload state. You're actually operating less overall brake horsepower, but a test and balance guy can easily get in there and dial that system back to that design 10,000 CFM. So it's a non-overloading design. And this is the reality of most product selection, unfortunately. Again, many jobs come across my desk laid out at a 1/2 inch and a 1/4. We're victims of always overestimating or compensating for static. And if it's not there, that system's going to move too much air. And the only solution to that is slowing these fans down. Now, the downfall to anything on a forward curve fan, which is still going to be in your 25,000 CFM and higher airflow ranges, is anything that's above 10 horsepower, you're now in fixed pulley arrangement. So there's no more drive adjustability on the motor side to be able to slow a fan down by turning a pulley in or out a 1/2 a turn at a time. They're fixed pulleys. So if you're in that overload state, first off, you're throwing a dart at the system to just try and calculate what shivs need to be changed out if you don't have a VFD. And then you're trying to balance the system down from there. So another benefit of mixed flow fans, direct drive fans, but also just considering putting VFDs on these very large systems that have fixed pulley arrangements, and considering putting the drives built in to just simply slow down that fan speed by changing the frequency output to the motor rather than having to change out belts and pulleys. All right, so that's the big, I guess, news as far as moving airflow. Just keep in mind, again, direct drive fans as a standard up to around 22,000 CFM. Forward curve fans are still very efficient in the higher airflow range, and we go all the way up to 65,000 CFM with one single makeup air unit, one big 50 horsepower motor driving 2 fan assemblies. The belt-driven fans do still exist in the higher airflows. All right, now cooling with makeup air. I kind of brought this up at the beginning where cooling is just not as common in makeup air applications. We really see this around the kitchen market. And the reason for that is because everything coming into that building is typically being exhausted right back out. So it's kind of a waste of energy, whether you're looking at heating or cooling. But we'll talk about, and so just don't confuse this, I guess, with a general DOAS or a dedicated outdoor air system application. We're looking at really sensible cooling only. So measuring outside air temperatures, what are we at? If it's 80, 85 degrees outside, maybe we should consider energizing one circuit of cooling, bring it down 10 degrees to about 70. If it's 90 outside, we'd bring on a second compressor and bring it down to roughly 70 degrees. So you guys are in a unique market out there in Washington. So when you guys get a little warmer, you guys are definitely a little less humid. Here in Wisconsin, this type of technology doesn't work. When we get hot, we get very humid. So trying to introduce water to already saturated air does really little to nothing as far as effectiveness. But in your area, we're talking 90 to 95% cooling effectiveness, depending on what your humidity and what that wet bulb temperature is outside. The benefit of evap cooling is airflow is pretty much limitless. You can go all the way up to 64,000 CFM with one single makeup air unit and introduce evaporative cooling. And again, the efficiency stance on this, 90 to 95% cooling effectiveness, depending on that outside air. Now, as a standard, we're going to use Munter's Cell Deck media. Glass Deck is available. That's if you need the fire rating on that as well. So they're really the best in the industry. Full stainless steel surround, full stainless steel drain pan. And then the biggest thing I want to highlight is the optional automatic drain and fill kits. I'm sure Dorse has gotten in the habit of this, but just something to keep in mind. Auto drain and flush is pretty important from a maintenance stance, because once you're introducing water into the airstream to effectively cool it, well, what are you left with in that pan if you're not doing some form of flush sequence? You're left with all the mineral content, or depending on whatever your water quality is, whatever's left. So water is being introduced into the airstream. So it's very important to do like an automatic drain and flush sequence of that pan to introduce fresh water supply to extend the longevity of that media. So it is something that we offer. It's an auto drain and flush kit from the factory once a day for 5 minutes. It'll introduce fresh water supply and flush that pan out. So just a fun little fact there. Other things too, not many manufacturers do this, but we do have built-in 2-inch aluminum mesh filters have always been a standard, but now we do have optional MERV 8 and MERV 13 2-inch filter options before that media, anything up to about 13,000 CFM. PDX, so package DX cooling, some interesting changes are actually in conversation right now. That's actually a meeting that I just came from before this presentation. 2025, we're moving to a new refrigerant type. And that refrigerant type is going to be considered slightly flammable. So there's interesting conversations on that and how it'll be applied to our equipment in the first place. And we're in redesign phase right now. So everything currently at 410, all the way up to 8100 CFM. But it looks like we're going to be changing that overall design to about a max of 5,000 CFM with this new A2L R454B type refrigerant. That's really hits majority of the market that we're looking at for the kitchens. 5,000 CFM seemed to be a pretty good happy point. And since we needed to redesign the whole box, that's kind of where we ended up landing. Currently, the PDX or the condensing section hangs off the backside of our unit. We're actually looking at an engineered design, more of a V-bank module on the top of the unit now. So the units will get a little bit taller. So just interesting changes to talk about right now and discuss going forward for 2025. Current state right now is at 8100 CFM, but again, 5,000 CFM is probably going to be the top end of this when we come closer to that 2025 date.
Hey, Phil, I wanted to jump in real quick and just let everyone know that Greenheck also has an advanced line of rooftop air handling units, the RV unit, which does have the options for heat pump. The refrigerant change is already taking place, and those can go up to about 18,000 CFM. So what Phil is talking about is, again, these kind of economical light tempering units for cooling and heating. So that's why it's kind of focusing around that 5,000 CFM and less for that cooling for the kitchens. But when you do have those applications where you have larger amounts of outside air, we do have another model unit, and we will be doing a power hour session on that here in a few weeks.
Yep. So RVE, considered a more of a DOAS type. This is, again, like Chris had mentioned, more of the economical approach when we're just looking to take the edge off that outdoor air. Then that's where the RV model actually needs to be considered if you're looking at a little bit larger airflow capacity. So thanks for bringing that up, Chris. Lead digital scroll compressors are also available, just not very common for most makeup air. We're looking at variable speed compressors and everything like that for the model RV that Chris had mentioned. A little bit better temp control. Again, this is more of a low cost packaged option for more of your kitchen design. Just want to let you guys know that it is available currently for 10A, and we are looking at options for the new refrigerant change and the refrigerant type come 2025. All right, heating. This is the fun, interesting topic that we can talk about because Washington State fits that very unique market where electrification, the shift has kind of already occurred. I know Seattle, I think, has banned gas entirely, but I think that there's still work being done. Depends on where you are in that state, and I think that there are still workarounds as far as parts of the code, and depending on what the application is, where gas is still being entertained in certain applications. So we'll talk about both. It is interesting because the electrification conversation, it's going to take a little while, I think, for this country to actually be ready for it. There's I don't want to get too political here. And really what it comes down to is your availability, what your electrification or what your electrical grid looks like, where the electricity is being produced. I know you guys out in Washington State, it's heavy hydropower. So it's a totally different conversation than, say, something here in the Midwest. Our power plant that powers us here in the middle of Wisconsin is a 100% coal burning plant, and that was built 8 years ago. And we basically train coal over from the state of Wyoming. So it's the shift for us to move toward electrification, and it's a cost thing. So what's the cost of electricity versus the cost of and access to burning gas? So LP or natural gas, when we talk about gas fired, both of these units are set up to be capable of operating off of natural and liquid propane. So just a different realm and area that you guys are in, where electrical kind of makes more sense because your cost of electricity is a little closer to what the cost of actually consuming gas would be, but we'll kind of hit both notes. So from an electric standpoint, as far as makeup air goes, the RV model, again, as Chris mentioned, if you're looking for more of the heat pump style units, but if you're looking for just general electric heat options, we do offer an MSX model with an electric heater all the way up to 250 kW and roughly 24,000 CFM is what that equals out to be. An advantage from a manufacturing stance when we look at electric heat is it is single point power. Many other manufacturers will offer, because it's high amperage associated with these electric heaters, they'll offer a secondary power source. So you'll have a breaker required for your electric heater and then a breaker required for the makeup air. As a standard, as a manufacturer, we decided to go with one disconnect sized for the entire unit, make it a lot easier and lower cost for the installation side of it. So electrical, your electrician doesn't need to feed two separate supply wires up to the unit. Duct and room temperature control is available. These are SCR or veneer SCR controlled, so it's not just a toaster oven. It doesn't just turn on and give you full capacity. The reason there's the conversation with electrification is because of its efficiency. The efficiency on an electric heat is technically 100%. You can take every single usable volt going into it and convert that to the clean is where we can argue. And then again, cost standpoint as far as amperage, but technically it can be converted over to full usable heat. So again, depending on where you're actively, working on jobs, because I know that you guys aren't limited to probably just Washington State. Keep in mind that we do offer electric heating options. But if you guys are outside of the state, technically burning gas, if it's the lower cost option, probably going to be the one that makes the most sense. So that's what we're going to talk about. Well, what exactly are we talking about when we're burning LP or natural gas? We're talking about two different things. We're talking about direct gas fired and indirect gas fired heating. Direct gas, it's unique to the makeup air applications only, and it's because it's because of the application. It's because it's makeup air, and we'll kind of get into the weeds a little bit of why it's completely acceptable, and even the anomalies that happen with, all right, we look at indirect gas fired, and there's even a shift. I know the state of California is very common for doing this. They've stepped away from direct gas fired because of the concern of byproducts of combustion being introduced into a space, and the amount of CO and CO2 were indirect gas fired because of its efficiency. That gas is still being burned and it's still being vented out to the atmosphere, but much less efficient, and there's much higher levels of the CO and CO2. So interesting conversations. Direct gas fired, if you're looking at a gas heating option, definitely going to be the one that makes the most sense from an upfront cost, long-term cost, and overall operating stance. If you have access to gas, and again, your gas costs are less than what electricity would be. So the advantage with direct gas fired heating is there's no venting required. We still get this question from time to time. If a unit is installed inside, where does the venting go? It's literally a direct gas fired burner. So it's an open flame in the airstream. People forget that it's 100% outside air coming across that open flame burner. So technically 100% thermal efficiency, because you're taking 0 degree entering air and throwing it across an open flame burner. All of the heat loss associated with burning LP or natural gas is going directly into the airstream. Now, the concerns are what we'll talk about as far as the other things that are introduced into that airstream, but technically every single available BTU is where you want it, directly into the airstream to come into a space and get exhausted right back outside. Now, indirect, you do need venting outdoors. Most of these units are installed outdoors, so that's really not a big concern because it's just going to vent right out the atmosphere. But if it is an indoor installation, that's just considerations to have on the installer. You're going to need an intake pipe and a discharge pipe coming from that furnace to vent the flue gases out, and then at lower efficiency. So we're talking 92% efficient with direct gas fired heating versus 81% efficient. So that's typically what you're going to see in the industrial and commercial market. That efficiency is limited purposely because we don't want to condense inside that furnace. Condensate's not clean. It ends up basically eating away at heat exchangers, whether it's stainless or aluminum. And overall, you've got to worry about that water then when we're talking about higher efficiency applications. So 81% efficient, it would be considered a non-condensing furnace. So it can be mounted outdoors and you don't have to worry about heat tracing, bringing condensate back in and filtering it, neutralizing it, more installation costs basically. Fun facts as well, as far as efficiency goes on indirect gas-fired heat, you get more efficiency by basically putting more stuff in the airstream to reject more heat. Putting more stuff in the airstream basically just takes that efficiency and your gain of what you're burning gas at, and now it kind of marries it and takes it and transfers it over to your motor on your fan side, because you have more stuff typically to overcome on a higher efficient furnace too. So one other conversation piece on just why we limit efficiency on the indirect gas fired side, and why the push toward higher efficiency, we don't really see it. 92% efficient on the direct gas fired side. If it's makeup air, you can typically get away with a direct gas fired application. We'll talk about why indirect is even in conversation. So require outside air for direct gas. The advantage with indirect, you can do a full recirculated option, standard on DOAS type applications, where you can do literally no outside air and just recirculate 100% of that air across that indirect gas fired heat exchanger. Direct gas fired does require that outside air for bringing those byproducts of combustion down. Other advantage for direct gas fired heat, highest turn down in the industry, baked into the technology, 25-to-1 turn down. Now up to 16-to-1 turn down with indirect gas fired heat, but typically we see 4-to-1 as standard as far as pricing. So pricing on direct gas versus indirect gas, 4-to-1 typically versus 25-to-1 with direct gas fired. We'll talk about what that turn down capacity means. It's really tight temperature control is what it boils down to, but I got a couple slides that kind of discuss what that looks like further, especially with indirect gas fired. Now, the biggest advantage on the direct gas fired side, though, is definitely upfront cost and then overall operating cost. So depending on capacity requirement, how much airflow you're moving, 300 MBH and under, you're looking at still upfront 10% less typically for the direct gas fired equipment. And then as you increase that capacity requirement, you're going to see more of a gain on the direct gas fired side. Main reason being one single 6-inch burner section, 400,000 BTUs of capacity. To get more heat, you just simply keep growing 6-inch burner sections. We go all the way up to a 10-foot burner here at Greenheck, and that's where we can move 65,000 CFM of outdoor air and offer up to 7.2 million BTUs of heat. And regardless of where the electrification conversation goes there, I don't know where we're generating 7.2 million BTUs of available capacity in any other means right now, aside from burning natural gas or liquid propane. So that's another interesting part of, as far as like more of the heavy industrial applications. I don't know how much of that you guys are doing work on, but just something to consider. So when do we actually use indirect gas fired heat? Direct gas is definitely, if we're talking gas in general, it's the one that makes sense. But indirect exists really for this. The NFPA 54, the direct gas equipment, cannot serve areas that contain a sleeping quarters, anything defined as a sleeping quarters or a dwelling. But not many makeup air applications actually fall under this category. So we picture makeup air, picture wastewater treatment plants, general manufacturing, warehouses, kitchens. Not many of them can be defined as a sleeping quarters. So in most makeup air applications, if you have access to gas, direct gas really should be the forefront one to consider. Now, ones that are kind of funny and where indirect actually does fit in well, some paint process applications, custom paints, some paints actually, most paint booths, direct gas, no big deal. Some of the custom paint applications, the aldehydes, some of the things that we are bringing in with a direct gas fired burner can make a unique chemical reaction and cause what's called fisheye in unique paint applications. So that's also a shift toward indirect that is actually not related to this code whatsoever. But otherwise, sleeping quarters, a good example of this would be common kitchen area, say in a nursing home, or common living quarters where the kitchen is in the middle of the building and then the sleeping quarters are off of the wings. A firehouse is another great example, or hotel corridor ventilation or stairwell ventilation. Is it part of or connected to a sleeping quarters? That's where you need to consider shifting toward indirect gas fired instead. General rule, direct gas when venting for a process, which is most makeup air applications, and then indirect when venting for occupancy, which is where DOAS mainly comes into play. But if you need to entertain general makeup air and it is still considered occupancy, shifting toward indirect gas fired does make sense. So the reason why, obviously CO2. So CO2, in ASHRAE 62.1, you need to keep CO2 levels obviously low. And with direct gas fired equipment, it's obviously introducing CO2 right into the supply air. Now, this is where the picture kind of gets confusing, and I think where a lot of people step away from direct gas fired. And it's not understanding exactly what those levels of byproducts are and what the process is. So remember that if you're burning gas, it's the most effective form of gas heating in the industry, because you have literally 0-degree entering air coming across that open flame burner, heavily diluted by the outside air, minimal amounts of CO2, CO, and the scary stuff that's coming into that space. But remember the general application again. Yes, we're bringing in all thermal properties, which is the advantage. We are bringing in a slight amount of the stuff you don't want to be breathing in, but remember where it's going. It's coming in for process exhaust. So it's coming in, kitchen is a great example, hits the chef in the back of the neck, and then it gets exhausted right back outside. Now, most kitchens today, I don't know what this looks like in Seattle either with the shift away from and the move toward electrification, but most kitchens that you walk into, natural gas fired equipment is all over the place. You've got your ovens, you've got your fryers, you've got your grill. Everything is typically, most chefs prefer to cook over an open flame, and most of that's going to be gas fired equipment already. And you're already, everything is, the reason you have makeup air is everything is vented outdoors as part of that process exhaust system. Now, indirect gas fired obviously doesn't add CO2 to the supply air, but one thing to consider is that at 81% efficiency, if you're trying to talk about greenhouse gases and things like that, totally different conversation, because indirect gas fired at 81% efficient actually throws more CO2 out into the space than what your typical direct gas fired unit would do as well. So outside air safely dilutes the byproducts of combustion. And this is just to put it in real world terms and make kind of everybody feel a little bit more comfortable. And again, I know the shift away from gas, especially in the city of Seattle, but if we can still entertain it, and this is just to have a conversation, real world carbon monoxide levels, what we need to test to in order to put an ETL label on our direct gas fired equipment, 5 parts per million of carbon monoxide, 0.5 parts per million of nitrogen dioxide. That's what we need to test to, levels under that, where OSHA states that you could be exposed to for 8 hours, 50 parts per million of carbon monoxide and 5 parts per million, that's 10 times greater, and walk away completely fine. So that should hopefully set the story straight that what we are able to bring in and what we are allowed to bring in, this is an extremely clean burn, and again, heavily diluted with outside air. You can be exposed to 10 times greater than what that unit is actually bringing into the space before it's being exhausted out in the first place. So just to kind of set that story straight. Now, recirc, a lot of confusion around recirculation with direct gas fired. It can be utilized. It's called an 80-20 unit. So I'm hoping you guys can maybe see my cursor here too, but the 20% portion dedicated for this upper damper here. So this damper is the 20%. That damper, look at it as an inlet damper. Every time the unit is energized on, that damper opens, brings in minimum 20% outside air, and then the remaining 80% is this, what we call a mixing box. So it can either be the remainder of the outdoor air to do 100% outside air, or if this damper is fully closed, this one would be fully open. We can do a maximum of 80% return air, minimum 20% outside air, but then obviously anywhere in between. Great applications for general manufacturing and warehouse ventilation and warehouse heating, where you're bringing in a minimum of 20% outside air for fresh ventilation at all times, always churning air throughout that facility because the fan's always moving XCFM. It's just what's the percentage of outdoor air actually coming into that building. And that only changes when the pressure in the space changes due to an exhaust fan being energized, or in like a warehouse type situation, a dock door opens up. You lose pressure in the space. It naturally ramps up more outside air, but it's always discharging X for whatever temperature that you want for a discharge temp. And then no return air is allowed to pass across that burner. So there's a sheet metal divider that's dedicated for that 20% section, because we don't know what's going on in that space. If it's general manufacturing, what if it's wood dust? What if it's chemical products? We don't want that going across that open flame burner. So that is split air streams, just to make everybody feel a little bit more confident on that as well. So now also another conversation piece with direct gas fired is variable volume. So a lot of times now when we talk about general makeup air, you don't always need to move 10,000 CFM. That's your worst case design. But if you can move the exhaust down as well as the supply, obviously that's overall operating costs significantly to drop that requirement down. Kitchen's a great example for this. You order a unit at say 5,000 CFM, large kitchen application. We allow up to 50% reduction in our same box on a direct gas fired unit. And if you can reduce that whole system down, you're bringing in 50% less outside air, you're physically moving 50% less air on your exhaust and supply side. So obviously your overall operating costs will come down significantly. Most other manufacturers, especially with direct gas fired equipment, are limited to about a 20% reduction at best. Now, how do we do that with direct gas fired heat? We do it with this barometric bypass damper and the requirement of the airflow across that burner. So the barometric damper located right here underneath this burner section, that allows for the at design airflow, that damper basically cracks open and allows that pressure drop to stay the same at design. And then as you start to lower or drop the required amount of outside air, that damper starts to kind of creep close, forcing the excess air up top, always maintaining a certain percentage of a certain pressure drop across that burner for good, safe, clean combustion, no matter what, at design airflow or minimum airflow. So air velocity needs to remain constant across that burner for that good quality combustion. Now, also with a direct gas fired system, this is a typical operating or a system curve, that blue dashed line going all the way down to 0. It's unique with direct gas fired because there is that minimum pressure drop requirement for your burner section. 0.65 inches is required to properly and effectively burn the byproducts of combustion and allow for heat. So that 0.65, it's actually a different operating point with direct gas fired systems. All right, so now let's shift toward indirect gas fired. So indirect, I mentioned the turn down capacity. Well, what exactly does 4-to-1 mean? Now remember, direct gas fired has 25-to-1 built in, but the math is kind of going to be the same here. So when we're talking about what 4-to-1 turn down actually is, you design a system around 6,173 CFM. You want to discharge 70 degrees on a worse design day where it's 10 degrees outside. Furnace capacity, 400 MBH required to get you that temp rise of 60 degrees. That's a typical design. Now the 4-to-1, your temp rise, you take your temp rise, divide it by that first number. So 60 divided by 4 gets you your minimum. Where this gets unique is we're getting into the season right now. We're finally, spring is here. So those outside air temperatures during the early hours and late hours, maybe they're a little cooler, but maybe you only need a 10 or a 15 degree temperature rise. Well, what does 4-to-1 mean when you actually have a 60 degree rise and what your minimum is? What if you have a 60 degree outdoor air condition and you still want to be able to discharge that 70 degrees? Well, with 4-to-1 turn down capacity, 60 degrees divided by 4 is 15 degrees. That's your minimum. So your minimum capacity now is still overshooting what your design discharge air temperature is. So that furnace is going to cycle on and off on those shoulder days. So high turn down capacity, very crucial. The higher the turn down, 25-to-1 built into direct gas fired equipment, now up to 16-to-1 with indirect gas fired, but obviously more costs associated with that. So typical is 4-to-1, and that's the math and kind of what that actually means. So the higher the available turn down, the tighter the temperature control that you'll have no matter what the outside air temperature is. So what does that look like? Furnaces fire on with an indirect gas fired heater. They fire in high fire, then they modulate down to its lowest firing rate. So here we're on in high fire, it modulates down. Our set point, we only need a 5 degree minimum temperature rise to achieve whatever our leaving air temperature is. Well, since it's 15 degrees is our minimum, it's firing at low fire. It can't do anything else but to shut down. So then it shuts down and then it's bringing in whatever outside air has to offer. There's a cool off period required and then we're below set point. So we fire back on in high fire and then it's just a vicious cycle. So the killer of all equipment is obviously furnace cycling, equipment cycling. Anytime you can just energize a relay or energize a unit and maintain, always going to be an advantage. So 16-to-1, this is what that looks like. Furnace fires on in high fire. Your minimum temp rise now, if you do the math on that, 60 divided by 16, 3.75. If you only need a 5 degree rise, it can just sit there in low fire and just maintain all day long. And remember, 25-to-1 built into direct gas fired equipment. Now, the other thing to consider is, well, what about airflow? We allow 50% reduction in that same box in airflow. Now, what does that look like? We reduce our system down to same box. we're designing it for worst case scenario. You have that same 60-degree outdoor air day and you're at minimum airflow in that box right now. You just doubled your available temperature rise. So now that thing's going to cycle even more. So even your design temperature rise of 60 doubles to 120 degrees. And then at minimum at 60 degrees entering air, your discharge air minimum is 90 degrees now. So that furnace is going to cycle on and off a lot more frequent if we're looking at lower airflow in that same box as well. So just all things to consider. Okay, so airflow considerations, most applications, I explained this kind of earlier, more of a 1-for-1. So we're exhausting X CFM, therefore we need to bring in X CFM to roughly balance out that airflow. Slight negative, slight positive in some cases. Now where you want a slight negative, kitchens, parking garages, paint booths, hazardous storage, wastewater treatment plants, things like that. That's where you typically want to try and size for larger exhaust and a slight negative pressure as it comes to your building. Now, positive pressure applications where you want your makeup air to exceed whatever you're being exhausted, generally for cold air infiltration, warehouses and general manufacturing, more of the space heating functionality trying to push infiltration out. Now, variable exhaust rates, I kind of talked about the two different options and how we do this. It's very common, obviously, to reduce energy consumption. The lower you can move airflow or reduce airflow, the less outside air you're bringing in that you need to heat or cool, and then obviously physically move with power, the horsepower of your fan. So variable volume or recirculation, that's kind of your two options, being able to physically reduce airflow up to 50%, or if you can recirculate 100% in an IGX selection or up to 80% with a direct gas fired unit, the more air that you can recirculate, the less outside air is being introduced, therefore a lot less on the gas side of things. If you're looking at or just general heating application, less outside air to heat because you're bringing in already and just rotating through that 65-degree space condition already. So exhaust tracking, very common with single exhaust fan type systems where we're looking at just tracking, all right, if this exhaust fan is on or if this exhaust fan is running at this speed, the supply fan will run at the same, typically for a more one-on-one type scenario. Now, building pressure control is more of where you have open spaces. I kind of mentioned the whole warehouse design, or if you have multiple exhaust fans, it's very easy to achieve a sequence when it's just changing. It's effectively changing the percentage of outside air or volume of outside air with a variable volume system, just based on a pressure setting instead. All right, so this shifts toward our space heating conversation here. So warehouses, what is green heat? Green heat is a basically marketing term for Greenheck, but it's our space heating unit. So our space heating unit is exactly what I described with a direct gas fired DGX model, except now it's going to cycle on and off and typically not be married to an exhaust system. So now we're superheating the air, effectively bringing in outside air for fresh ventilation, superheating it to 140 degrees, and the space condition is what's driving that enable and disable. So once we satisfy the space condition, the whole unit actually disables. So direct gas fired heating, 92% efficient, 100% outside air, and 140 degree max temp rise or leaving air temperature to effectively get that space temperature up to 65 or 70 degrees as fast as possible, and then cycle off. So fixed sizes that optimize the cost per BTU. The advantage of green heat is if you guys play around in CAPS at all, our selection software, if you search the model green heat, if you want to do more of like a design build type application, you got a large warehouse or general manufacturing facility, we've got built-in design load skin load calculations for you in the green heat selection software. All we need is perimeter. We need what the roof height is, how many dock doors you have, how many service doors you have. You can change the percentage of activity. You can kind of fine tune that building, insulation values of ceiling, insulation values of walls, and we'll actually calculate what your skin load loss is in your building to tell you what the BTU requirement is for effective space heating. So give you the minimum recommended recommendations for how many units would effectively satisfy that space, but also just use that BTU number for whatever you want. If you want to go to electric heat pump, it'll do its free design build software built into our Greenheck selection. So just keep that in mind. Again, it does populate though. Amazon distribution facility, for example, 1,000,000 square foot facility, you can get away with as little of 8 units to effectively heat and ventilate that very large 1,000,000 square foot facility. So very effective way to approach both ventilation and the heating side for these very large spaces. And they'll cycle on demand for whatever that space condition is, very similar to your home furnace. So, and that high temp, more usable BTUs per CFM at the elevated discharge air temperature.
Hey,
now, I don't know if it, yeah.
Hey, Phil, this is about your 5 minutes.
Yep, I got it.
Heads up.
We're on, yep, thank you. Just wrapping up here. So, in case you've ever heard of Cambridge, just to keep in mind now what the Greenheck selection actually is. If you've ever heard of the Cambridge model, that is exactly basically the same thing. So Cambridge is a space heating direct gas fired unit, as well as our Greenheck model. Now, just to clear up some confusion that often happens out there, Cambridge will specify, so if we see this stuff on a schedule, they specify inlet air because their blower is before the burner section. So it looks very confusing on a schedule for the 1-for-1 when you look at a direct gas fired Greenheck unit. So we'll specify the 8,266 CFM being delivered into the building. When truly, once that airflow is actually being heated up, we're both providing 1,200 BTUs or 1,200 MBH into that building, but effectively at 160 degrees or 140 degrees. And truly, they're delivering that airflow at 7,487 versus our 8,266. So yes, it's slightly higher airflow, but don't get too tripped up on what that looks like on paper, because remember that it's inlet CFM that Cambridge unit is going to look at. So there's a lot of confusion around that. BTUs are BTUs. Again, it's just being introduced at 160 versus 140. Conversation there. People can argue there is definitely more BTUs available at that elevated discharge air temperature. I can't argue with that. That is why we're still slightly higher on the airflow, but slightly higher airflow means slightly higher on the air changes, as well as a little bit longer runtime for it to satisfy that space condition, but also provide a little bit more fresh air ventilation to that space. And 140 is going to climb to the ceiling a little bit less time than what 160 degrees is. So, but otherwise it's pretty much 1-for-1. BTUs again are basically BTUs in the end. Don't get too confused what it looks like on paper. All right, exciting stuff for us to shift toward microprocessors. We're almost seeing this as a standard. We haven't officially made that change yet, but I just want to make everybody aware of that. Huge advantages here because really everything is built into these controllers. Very easy field changes. If you order a unit as room temp control and want to go discharge temp control, everything is built into these controllers. Built-in commissioning, that's another huge advantage that we have. We get a lot of positive feedback on that. Walk a guy through an indirect gas fired startup, walk a guy through a direct gas fired startup with simple yes and no questions. We've got beautiful YouTube videos out there to walk you through what's the menu actually asking you to do, and then just simply answering yes or no to the questions as you progress through. Alarm logging. An alarm light will flash at you, but it's not going to flash 2 and 3 and go and find a book and figure out what a flash code of 2, 3 means. It'll literally, you push the alarm button, it'll read out exactly what that alarm is, up to 100 different alarms, logged, the time stamped. It's just, there's huge advantages with these microprocessors. They can be standalone and it can be operated with a building management system as well. Confusion there always too. People think, oh, I got a microprocessor, I need a building management system. Not the case. These microprocessors can take care of themselves, internal set points, very easy menu navigation to walk guys kind of through starting up this equipment. So pretty slick stuff. Built-in web UI or web user interface. This is what it actually looks like if you were to plug this in. This is built in, no charge. Web user interface, if you can connect to an Ethernet cable, you can directly communicate and talk to that unit, make changes, and view this little diagram that kind of shows you the status of the unit, what's your coil doing, what's your leaving air temp, what's your incoming air, and you can make changes, you can view alarms, you can do trend data and things like that. local network stuff. So you take your internet connection, Ethernet cable, land it on the controller in the unit. We will punt out the IP address for you to use that on your local network, and this is what will come up and populate. Now, BMS, different conversation. We need to know, is it BACnet MSTP or BACnet IP, and we can give you a protocol to talk to a unit. There, if you want to control a unit from California and you want to control something in Maine, that's where BMS. If you want local compatibility, that's where the web UI kind of comes into play. Exciting stuff here. This is really the slide I kind of wanted to get to is we finally introduced a touchscreen display with our microprocessor now as well. We had a lot of feedback. People always wanted remote panels with microprocessor, and we had remote display options, but it was like basically all the bells and whistles that you always got at your fingertips, and not everybody in the space wants that, right? It's you have to be familiar with the menu navigation. You'll still have that up at the unit and up at the controller, but now more of a handoff auto type situation, alarm logging, ability to lock this thing, sensing capabilities. So wall mount options, we're going to have NEMA 4X rated enclosures. They're plastic covers that have a clear cover on it, so you can still see this stuff. And again, whether you want fingers on this or not, it's a lot less to this than what the full microprocessor is. But now we have remote panel options essentially with our microprocessor. So new touchscreen display. Pretty excited to make this announcement and give you guys the future of where we're going and pretty much standardizing on microprocessor options as a future. Cost has come down significantly on this stuff. So that's it, guys. Thank you very much for your time. I appreciate it. I know I cut you right into 3 o'clock here, but do we have any questions that came through?
Thanks a lot, Phil. That was really great stuff. We do have one question from Kristen. She's asking if the makeup air units have a thermal rating.
A thermal rating. So I don't necessarily know if I'm following exactly what's being asked there. So we can discharge up to 140 degrees. So that's what our cabinet can kind of handle. Thermal ratings, there we have insulation options. So you can do double wall type insulation, typically about an R3, R4 that you're going to see, just typical 1-inch insulation in most makeup air. If you're looking at better thermal ratings, you're looking at the DOAS models, RV, RVE, foam injected panels, 2-inch R13 at that point. So makeup air, not as great as far as the insulation value. Maybe that's what she's looking for.
She did just post a little bit of a follow-up, maybe clarification. She said, or do the makeup air units have to comply with a standard regulation or efficiency metric? If that makes it any clearer.
Okay. Chris, you know at all maybe possibly what she's referring to?
No, and Kristen, if you want to, feel free to email us or give one of the Dorse reps a call. We can get it. But in terms of regulation, obviously these units are certified, ETL listed. Every overseeing body that needs to be certified, and efficiency metric. Greenheck wouldn't produce these units if they didn't comply with government and regulatory standards. But we're happy to answer any advanced questions. You can
I think the most important piece is we are ETL certified. And I mean, that's the biggest piece of that is what byproducts of combustion we're actually allowed with, say, direct gas fired equipment and things like that. And then as far as efficiencies, 92%, that is the most efficient form of gas heating. And I don't necessarily know what the governing standards are going to be that Kristen's looking for. But yeah, anything that you have, feel free to send that our way, and we can dig into that a little bit further.
That's great. I think we've given people a chance to, I'm not seeing any more questions, and I know we're a little bit over time, so thanks a lot, Phil.
Beautiful. All right. Well, thanks a lot, guys. Thanks for the invite here.
Glad to have you. For any of you still around, we're going to be doing another presentation next week on fan fundamentals and motor fundamentals. We'll get into FEI, probably some FEI, FEG things as well. So we'll see you next week.